Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 30th, 2025, about 2 days ago. In this paper, the authors show that deep sequence models do not just perform associative lookups. They synthesize a global geometric memory, with transformer and Mamba models achieving near 100% accuracy when trained on 75% of the 10,000 paths, handling path length 10 in graphs with up to 5 times 10 to the 4 nodes. The paper is titled, Deep Sequence Models Tend to Memorize Geometrically. It is unclear why, and as we will see, the implications for how models store facts are quite significant. Alright, the introduction set the motivation. Figure 1 contrasts associative and geometric memory across 4 graph types, including path star, grid, cycle, and irregular. The left column shows a transformer with frozen embeddings, which scatters nodes arbitrarily like a lookup table. The middle column shows learned transformer embeddings that organize by global graph structure, so multi-hop relations become near neighbors. The right column with node 2vec shows an even cleaner geometry, signaling practical headroom. Well, Figure 2 illustrates the in-context path star setup, with training examples on top and test examples below. Each panel shows a star of paths with randomized node labels, plus a text prefix that lists the adjacency bigrams, so the model only sees local edges. The start and goal nodes are marked, and the target output is the full route to goal path. Success requires reconstructing the unique chain by effectively walking backward from the goal, which a left-to-right next token learner struggles to do. So, Figure 2 set up the in-context version. Figure 3 presents the in-weights path star task. The graphic shows a fixed star of length L paths, where colors mark train paths, test paths, the start, and the goal, so the model must store the entire graph in its weights. The right panels list 2 training streams, edge memorization, which feeds adjacent node pairs, and pathfinding, which gives a leaf and the full route to leaf sequence. Unseen leaves form the test set. So, Figure 3 laid out the in-weights task. Figure 5 shows the contrasting in-context behavior. Left panel reports full path accuracy stuck near chance across small graph sizes, which signals no reliable planning. The middle panel plots token accuracies over training and reveals a right-to-left learning cascade, so the model exploits easier later tokens first. The right panel shows the hardest first token fails in isolation, underscoring why in context, pathfinding collapses. Alright, Figure 4 presents the in-weights results, which show strong success on large path star graphs. The left panel reports full path accuracy near or at 100%, even with long paths and tens of thousands of nodes. The middle panel plots token accuracies over training and shows no right-to-left learning cascade, so gradients from future tokens are not required. The right panel shows the hardest first token achieves high accuracy in isolation, indicating true implicit multi-hop reasoning. So the previous figure established strong in-weights accuracy. Figure 6 shows why that performance emerges. The left heat map displays a sharp diagonal, which means leaf and first hop embeddings from the same path align closely, signaling a shared global structure. The middle U-map projection reveals clear clusters by path identity, so multi-hop neighbors sit near each other. The right heat map, trained with only edge memorization, still shows a faint diagonal, indicating a weaker but present geometry that arises from purely local supervision. So, 2 takeaways stand out. Deep sequence models often form a global geometric memory that collapses multi-hop reasoning into a near one-step lookup, and this structure arises without obvious pressures, pointing to a spectral bias seen in node 2vec. The implication is clear. We can engineer models to be more geometric, improving knowledge storage and control. Thanks for listening. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.